Great, thanks. Yes, so I guess I will be building nicely off of that talk. As Tad mentioned, I will be talking a bit about the way we define a selection for the Gaia-Sausage-Enceladus, and I'll be sharing some newer work that we've been doing on the chemical abundances of both the Gaia-Sausage-Enceladus and Sequoia. Okay, so I think Tad introduced it very nicely, but basically we have the Gaia-Enceladus population and the Gaia-Sausage population that were identified in these kinematic spaces as essentially an overdensity, and also found to have alpha abundances, at least, that are different from the main Milky Way populations and indicate that these stars formed in a system that was lower mass than the Milky Way. And since then, there have been several papers identifying increasingly more populations that are likely to be accreted in the Milky Way halo. I'm just gonna flip this figure on the right for you so that these axes are saying the same thing now, but as you can see, there's been a lot of new populations identified, and so I'm basically just going to focus on Sequoia, which is a high energy retrograde population, and the Gaia-Sausage-Enceladus. Okay, so the paper one in this sort of mini series was looking at a combination of SkyMapper data and Gaia RVS data. So SkyMapper is a photometric survey that gives us pretty good metallicities, photometric metallicities, for a really large number of stars. So with this photometric data, you can get these metallicities for a larger number of stars, especially pushing out to the halo than we could with spectroscopic surveys right now. And combined with the RVS data, we could get full kinematics for these stars. So we ended up with a sample of about 900,000 stars. And we're focusing in these 4 kinematic spaces on basically this elongated overdensity that is the Gaia-Sausage-Enceladus population. So when searching for Gaia-Sausage-Enceladus, we basically had 2 things that we were keeping in mind when trying to identify where this population was sitting. We were looking for a single population of stars, and we were assuming some sort of chemical homogeneity in the stars of that accreted population. So that was the driving assumptions that we were working with. We also ignore any possible chemical gradient in the kinematics of the stars, but I think that's an interesting possibility to look into, and has been explored a bit in Naidu et al. 2021. Okay, so this is basically the main figure from paper 1, where we identify this kinematic selection of Gaia-Sausage-Enceladus stars that has now been pretty widely used, which I really appreciate. So this is the radial action, the square root of the radial action as a function of angular momentum. And we basically binned up the stars in this space just symmetrically around 0 angular momentum. So the retrograde stars here are the red boxes and the prograde stars are the blue boxes. And within each of those boxes, we looked at the metallicity distribution function of stars that lie in that kinematic space. And so the way these figures transfer is basically that the prograde and retrograde boxes with the same radial action lie in the same cumulative metallicity distribution panel over on the right here. And we found that if we look at just the highest radial action boxes, so 1 and 2, we find that essentially both prograde and retrograde stars in this space have an identical metallicity distribution function with a mean metallicity of about minus 1.17. However, as you go towards lower radial actions, you get the samples of stars have quite different metallicity distribution functions, both from boxes 1 and 2 and different in the prograde and retrograde stars. So from this, we sort of decided that from previous work, this is approximately, we expect this box to contain quite a few of the Gaia-Sausage-Enceladus stars. And from the metallicity distribution functions, we concluded that probably these lower radial action bins have increasingly more contamination from either Milky Way in situ stars or other accreted populations. And so we identified boxes 1 and 2 as sort of the cleanest selection of Gaia-Sausage-Enceladus stars. And actually, if you look at this metallicity distribution function of these stars in bins 1 and 2 in red, and compared to just a random Gaussian distribution of stars with the same mean metallicity, with basically a 1 sigma and 2 sigma distribution of the metallicity uncertainties, we find that it's a pretty narrow distribution of stars in this population. So in paper 1, we also used this mean metallicity that we found to try to constrain the mass of the Gaia-Sausage-Enceladus progenitor using a mass metallicity redshift relation from Model 2016. So this is simulation work of isolated dwarf galaxies. And so from previous work, as Tad mentioned, from Gallardo et al. Specifically, we think that the Gaia-Sausage-Enceladus probably fell in about 10 gig years ago. And so that was basically the redshift that we used to look at for these relations. Here we have the relation for a dwarf galaxy that has a metallicity of -1.4, -1.2, and -1 dex. And so you can see there's quite a range of masses depending on the metallicity that you get, and therefore a range of masses depending on your uncertainty in your metallicity. But we concluded that the mass of the progenitor falls somewhere in here with a log mass of somewhere between 8.85 and 9.85 solar masses. And this is roughly consistent with other works that either use also a mass metallicity argument or some other argument based on the globular clusters or the number of stars found in the population. So our paper 1 conclusions are essentially that the selection of a clean sample, we provided this clean selection of a sample of Gaia-Enceladus stars using the SkyMapper and Gaia RVS data. We found that this selection of stars had a pretty narrow metallicity distribution function that peaked around -1.17. This population was consistent with the blue sequence of the dual sequence halo that's been explored quite a bit in the Gaia data. We constrained the mass of the progenitor, and basically through our work, we did this metallicity distribution function binning in the other 4 kinematic spaces that I had showed at the beginning, and basically found that kinematic only selections can be quite prone to contamination, depending on how you bin your space. And so, these boxes 1 and 2 certainly don't contain all of the Gaia-Sausage-Enceladus stars. They potentially do contain non-Gaia-Sausage-Enceladus stars, but the other boxes probably contain a higher fraction of non-Gaia-Sausage-Enceladus stars than these high radial action bins. Okay, so now I will move on to paper 2, our latest work that came out a month or so ago. So now we moved on to using basically two large samples of stars. The first one is just the Gaia DR2 RVS entire sample, and that's shown in the top panels here. Again, these are those 4 kinematic spaces that I flashed at the beginning. And then our other sample was APOGEE DR16 combined with Gaia DR2 for the kinematics and parallaxes. So these samples were both constrained to have 20% parallax uncertainties, removing stars with various quality flags. And for the APOGEE sample, we focused on the giants only. And so for the Gaia-Sausage-Enceladus population, we used the selection that we developed in paper 1. However, we also looked at the Sequoia population, and for that we used a selection based on the Mayon 2019 work. So in these spaces, I'll just go through what all these highlighted populations are. The blue one is the Gaia-Sausage-Enceladus. You can see from this, again, this radial action versus angular momentum space, this is the selection that we had developed before. So both in the RVS data and in the APOGEE data. Sequoia populations are shown in sort of the red and the pink, and we tested 2 different Sequoia selections, which I'll go over in just a second. You can see a couple interesting features in these diagrams. We have this overdensity that's highlighted in green in all panels. This is the globular cluster NGC 3201, which has been suggested that it may be associated with the Sequoia population. There's some work that says it could be either Sequoia or Gaia-Sausage-Enceladus. So we do a little bit of an inspection of those stars. And for people who like to point out overdensities, you might notice this one as well, which pops up in a couple of other panels. This is the globular cluster M4, but we don't really explore that one. It just really stands out. Okay, so coming back to the Sequoia selection, sorry. This is the action space map that is presented in the Mayon 2019 work, where they use this space, which is basically a combination of the different action parameters. And they choose the Sequoia population to be stars that lie in this highly retrograde space over here, whereas they choose Sausage-Enceladus stars to be in this, highly radial straddling zero angular momentum space. So here are our Gaia RVS and APOGEE samples in this same radial action space. Sorry, what do we call it? Action space map, right? Okay, so in both panels, I'm showing the red outline is the Sequoia selection, and there are various selections that we inspect. The light gray line is the same Gaia-Sausage-Enceladus selection that the Mayon work uses. I'm highlighting here in blue the Gaia-Sausage-Enceladus members that we select using our paper 1 selection. So you can see that they fall in a similar region, but the selections are not identical. So coming back to the Sequoia selection, this dotted black line shows the original Mayon selection region. We decided to, working off of an assumption that NGC 3201 may be associated with Sequoia, those members are highlighted in green here. And we found that they actually extended in this this J theta over J total space. They extended a bit farther than the original selection. So we chose to bump out that Sequoia selection a little bit to see if, extending that space to include all of the cluster members would also give us more Sequoia members. And initially we found that there appeared to be quite a bit of contamination in that space. So then we also chose to test a more conservative selection. So we call these two the Sequoia 06 and the Sequoia Selection. And I'll be showing chemical abundances using both of those selections. Okay, so first I want to talk a bit about the age work that we did with these stars. With the Gaia RVS sample, it's quite a large sample, which is nice. Unfortunately, there are not metallicities for a lot of these stars, so we did some assumptions here. But with such a nice, large, deep sample, we have quite a few turnoff stars for both the Gaia-Sausage-Enceladus and the Sequoia populations. So here I'm just showing color magnitude diagrams for the RVS samples. Here we are highlighting the turnoff region, and we have parsec isochrones overlaid, both of which have an initial metallicity of -1. So this is to account for potential atomic diffusion happening in the subgiant stars and also some alpha enhancement. And we have isochrones of 10, 12, and 14 gig years overlaid here. And you can see that most of the stars are consistent with having an old age. Even just by eye from these isochrones, you can see that perhaps the Sausage-Enceladus stars are a little bit younger than the Sequoia stars. So to try to get a little bit more precise with our ages, we applied the Salhult and Lindgren 2021 sample age distribution method that Christian talked about yesterday to these Gaia RVS stars. And so since the RVS sample doesn't have metallicities on its own, we assumed basically a metallicity distribution function as a prior, which we got from our APOGEE sample of stars selected kinematically in exactly the same way. And so the APOGEE sample has quite good metallicities, and those distributions are shown here. And basically we just use these as a prior and apply that to the sample of subgiant stars from the RVS sample. And so here we find that basically the sample age distribution, as Christian demonstrated yesterday, gives you a much narrower and precise idea of what the mean age of these stars are. And we find that both Sausage-Enceladus and Sequoia are old, as expected just from the by eye isochrone method. And we see that Sequoia has a mean age of somewhere between 12 and 14 gig years, whereas Sausage-Enceladus has a mean age somewhere between 10 and 12 gig years. So Sausage-Enceladus is probably a little bit younger. There's also a bit of a hint here that Sequoia may have some, either a small secondary younger population, or this could be contamination from Milky Way disk stars.
3.5 minutes left.
Thanks. Okay. And so since this conference is sort of focused on Gaia, this is not in the paper, but we quickly checked yesterday, and there was a small sample of Sausage-Enceladus stars, subgiant stars in Christian's total sample. And so here I'm just flashing the metallicity distribution and the age distribution of those subgiant stars in Gaia for Sausage-Enceladus. And basically these are consistent with what we found using both RVS and APOGEE. Okay, so now I want to show you the APOGEE elemental abundances. I have the Sequoia 2 selections here in the corner in case you want to refer to that. But so here we have magnesium over iron for Sausage-Enceladus stars in blue. Sequoia stars here in red. This is the larger Sequoia selection with the cluster NGC 3201 shown in green. And in the bottom, we have the smaller, more conservative Sequoia 06 selection. We have magnesium and aluminum on the right. And the black contours show Milky Way disk population just for reference. So we find that Sausage-Enceladus forms a really nice sequence, both in magnesium and in aluminum. And this has been magnesium, at least, has been shown a lot in other samples, so that's nice and consistent. And also that it has basically a lower magnesium abundance than the in situ Milky Way disk stars at a given metallicity. We find that the Sequoia selection actually looks quite complex. The larger sample seems to show definitely at least 2 populations being selected here. And that it's possible that the cluster could belong to Sequoia. There's sort of the magnesium abundances are consistent with the lower track in this larger Sequoia space. However, if we look at a more conservative selection of the Sequoia stars, a lot of that lower magnesium track goes away, and many of the stars are actually consistent with sort of a low metallicity extension of the Milky Way thick disk. And similarly, Sausage-Enceladus has pretty uniformly low aluminum abundances, and the picture is a bit more complex with Sequoia. And in fact, the Sequoia 06 population is perhaps even consistent with sort of a chemical evolution of a low metallicity Milky Way stars. And also there's been some abundance work shown by Diane Feuillet. I think you guys heard about that this morning in Australia. So we have a couple other elemental abundance spaces that we show. I'll just point them out very quickly. We have oxygen over aluminum, where both samples sort of sit apart from the Milky Way population, but aren't very obviously separated. we have magnesium over manganese as a function of aluminum over iron. And this has been pointed out before. Here in this space, the Sausage-Enceladus stars clump very nicely in this region of space that's been suggested to hold accreted stars. However, the Sequoia population doesn't really seem to clump in a similar way. In this case, I'm only showing the smaller Sequoia Selection. In aluminum over iron as a function of magnesium over hydrogen, we see actually that Sausage-Enceladus shows a very nice sort of natural break in the sequence in this chemical space. And so we actually apply this cut here to select chemically accreted stars and separate them from potential Milky Way in situ contamination stars. We apply the same cut to Sequoia, although it doesn't show the same natural break, but it's a much smaller sample. So then quickly, if we base our selection of accreted populations on these two papers, we would suggest these two kinematic and chemical cuts to select these Sausage-Enceladus and Sequoia populations. Although we talk a bit about how Sequoia appears to be a bit more of a complex population. We do come back to the mass estimates. Basically, Sausage-Enceladus doesn't change. And Sequoia is suggested to be lower mass than the Sausage-Enceladus progenitor due to that lower metallicity. Okay, so I will wrap up here. Essentially, selecting accreted populations is quite complex. We suggest that you use a combination of kinematics and elemental abundances. Definitely based on the elemental abundances of the Sequoia stars, there seems to be reason to inspect this population a bit further. And both populations have clear signs of being old and potentially actually older than the Milky Way stars with similar kinematics. Thanks, I'll stop there.
Thanks, Diane. I encourage everybody to make extensive use of all the features Zoom offers to virtually clap and show your excitement about the talks. Do we have questions already? Let me see.
I have one, if that's okay.
Yeah, sure.
I don't know if you can see me, Diane, but hi, long time to speak.
Yeah, hey.
Very nice talk. Thank you for this great talk about your results. I had a couple of questions. So one, if you go back to your mass estimates, so in these plots, you have redshift versus stellar mass, right? And so one thing I'm thinking of is current estimates of like the stellar halo, like the total stellar halo, estimate like recent work by Ted and Joe and things like that, around the ballpark figure of like in this scale about 9.25, 9.3. So then how would you be able, what would your thoughts be in this, that either the scale of or the estimates of these stellar masses are that you're getting, if you add the Sequoia and the Gaia-Sausage, surely they outweigh the total stellar halo estimates, right? And then if you add on things like the substructure R group identified, so Heracles, which given its alpha and iron abundances should be more massive than Gaia-Enceladus, then and then this off-global clusters and stuff, this number like gets blown out of proportion, right? So how could you account for all this? Do you think there's like missing stars in the stellar halo that we haven't found, or is there?
Yeah, I think it's a bit tough. I mean, you know, we purposefully give a pretty broad estimate of the progenitor mass based on these figures. You know, I mean, you know, we give at least 0.2 dex spread in metallicity possible, and that's essentially because, at least for paper one, the SkyMapper metallicity do have some uncertainties, but also, you know, this relation at least is based off of isolated dwarf galaxies, and I know that this redshift mass metallicity relation, I think it tends to give higher masses than what's seen in observed local dwarf galaxies. So I think it could be a bit of a systematic with the mass estimate method, or at least the isolated dwarf galaxy simulations. Yeah, I mean, I guess I don't know a lot about estimating masses of big galaxies, but I think there's a lot of uncertainties in all of it. But I think they're good questions to ask. And I think hopefully by coming at it from all these angles, we'll start to converge on both answers.
Couldn't agree more. Yeah, cool. Thanks.
Yeah.
I also have another question if nobody else has one. I find this really interesting.
Let's see. I guess if we have a short question, if anybody else? Otherwise, I guess if your question is short, you can go ahead if nobody speaks up now or raises the hand. Yeah, go ahead.
Okay. So this selection that Myung is short. This selection that Myung et al. Select for Sequoia, right? It spans this really large range of energies. I've been thinking about ever since they released the paper, like what kind of mechanism or accretion scenario would you have that would lead to having such a wide range of energies? So like, because some people argue that it should be cut into two things, right?
Right. Yeah. I mean, if you look, a lot of other works basically have this high energy section being one population and the lower energy being a different population. I'm not sure exactly.
So the reason I ask is because would that lead into the contamination you find from the Sequoia in the chemical space, maybe?
It could. I mean, we don't have that many stars, at least in APOGEE in the lower energy region. And we actually, I tried to look for a correlation between the energy and like the magnesium or the aluminum to see if basically these low energy stars had the higher aluminum and were consistent with being sort of contamination from the disk. I couldn't find a super strong correlation, but I do think it merits a stronger investigation. All of this paper too, we were trying to wrap up pretty quickly. It dragged out a bit longer than we thought, but all of this basically is just a jumping off point. I think there's much more that could be done with both of these populations, including modeling, chemical evolution modeling, numerical modeling of how you throw in the dwarf and get it to have these kinematic distributions. Yeah.
Thanks, Dan.